what the reciprocal space lattice mapping of the X-ray diffraction? Anybody done that? Okay, we call RSM. Anybody done the RSM work? Okay, so I think that's a very useful, but I think that requires some kind of background lectures I have to do. Otherwise, if I show some X-ray data and that you don't understand exactly what they mean, and that's why I may have to spend time on those things. So maybe at this point, I do not have a full package of those things, so I'll show you. But the next week, I'll cover more so that you can understand that both X-ray diffraction and the random data. So I'm going to start. Let me ask you a question. This is first, the fundamental of epitaxy. I think that's what I have one way. I'm going to talk about the atom-related control is another one. I think it's a kind of combination of it. But I'm going to start with some fundamentals of epitaxy, which is maybe you are familiar with this or maybe not. So I'm going to give you some basic background of this information, then how this epitaxy can be actually used, and then to design some materials, and then access, and then control the knob. So let me just start this, and then is not plugged in? Okay, it's plugged in. Why doesn't work? Oh, okay, that works. Slow. You know why this one doesn't work? Oh, okay, that's not the one. I know why. Okay, now it works. Okay, so the epitaxy is terms like coming from like an old Greek word, but epitaxy is the ordered growth of monocrystalline, I would say single crystalline materials, layer definite relation to the underlying crystalline substrate. Okay, that is the actually fundamental concept of epitaxy. So for example, your starting substrate is some kind of single crystalline substrate. Then when you lay down material on top, and then this one is kind of follows the structure or from chemistry underlying materials, and then grow single crystalline material. That's what we call epitaxial growth. And then you have, as I mentioned, that you have epitaxy has two types of epitaxy, heteroepitaxy or the homoepitaxy or heteroepitaxy. So, for example, heteroepitaxy is the growth of strontium titanate on top of strontium titanate, same material, and chemically same or similar to substrate, and that's the homoepitaxy. And heteroepitaxy is a growth layer different from the bottom of substrate in terms of chemistry, crystal structure, symmetry, and lattice parameters, and from the substrate. Okay, that is the heteroepitaxy. And then example is lanthanum aluminate on strontium titanate or strontium titanate on silicon. These are all good examples of heteroepitaxy. For example, these two are same crystal structure or perovskite structure, but in terms of symmetry point of view, this is the symmetry is a cubic, but this symmetry is a rhombohedral. Okay, so it's a lattice parameter of this one 3.905 angstrom. And this one 3.792 angstrom is a smaller than, and then this is smaller than this. So that means lay down this, clear you have a lattice mismatch. So this one has a component here, both chemistry, lanthanum, aluminum, strontium, titanium is different chemical element. Lattice parameter is different, and crystal structure is same, but symmetry is different. And the strontium, titanium, silicon is different too. Silicon is diamond cubic structure, and strontium titanate perovskite structure. The lattice parameter of this 5.4 angstrom is quite big, and strontium titanate only 3.905. But it grows beautifully epitaxially grow, And then how come you have such a large lattice mismatch grow epitaxially? The way it grow, rotate 45 degrees. You rotate 45 degrees, then the half of the diagonal, which is 5.4 angstrom squared root of 2, and this is basically roughly that the lattice parameter Schrödinger type. So you can actually match this, not perfectly cube on cube, but sometimes you rotate 45 degrees to match it. So that's a lot of interesting epitaxy. You actually see it, but it has a sometimes it's unimaginable. I mean, oh, this can grow on top of this, and this is an example. Strontium-10 silicon is totally different structure, and lattice mismatch like a 50% or something huge. It works well. Another one is strontium silicon. Really hate oxygen because once you got the oxygen, you're forming amorphous SiO2. And how come this oxide can grow silicon? That's one of the interesting magic of the epitaxy of this oxide thin films. So we'll talk about, it's a lot of general background epitaxy today, and this will be applied from today's all the lectures. Material we are dealing with is some kind of heteroepitaxial materials, and then superconductors, and then multiferroics, and 2D electron gas, and piezoelectric materials. All these things we are doing is almost all heteroepitaxy. And homoepitaxy is very, very limited because the use of same material on top of the same material is less likely, interesting, except certain types of specific experiments. So, why all the interest in epitaxy? Okay? Epitaxy is not only scientific point of view is interesting, but technologically very important in many ways. Okay? So, epitaxia grows is a standard processing technology in silicon device fabrication. So, for example, when you actually look at your microchips, and then when you have layers on top, you grow p-n junctions and those things. It's basically the same kind of p-n junction. And then on top of it, you grow another layer of germanium layer. And you have a lot of high electron mobility device. They have heteroepitaxy and germanium and silicon germanium. And then sometimes gallium arsenide, aluminum gallium arsenide quantum structured for lasers. They all use heteroepitaxial approach in semiconductors. And then that's technologically very important. All the lasers, you need a less defect because you have you need a very little defect. Otherwise, you cannot have the lasing in that material system. And then advanced epitaxial growth method, I think what we talked about here, permits the fabrication of extraordinarily advanced electronic photonic device structures. That's right, so lasers and all these things. And also, the science point of view is the extreme thickness control and modern epitaxial growth method, unusual and unique physical and chemical phenomena to be studied. That's what I'm talking about, a lot of things. So you have two extremes, but in between, and then thin film single crystal material that would be difficult possibly to grow as a bulk single crystals. And sometimes bulk single crystal cannot be grown because the phase diagram doesn't allow, sometimes segregation doesn't allow, and then that phase does not exist at all. But thin film allow you to grow metastable phases, which is thin single crystal, bulk single crystal, never form that phase. But heteroepitaxy is allow you to grow certain phase, certain structure, is never been able to grow by single crystal. Why? For example, bulk phase, structural bulk phase is, for example, is pyrochro phase. It's not the same as substrate perovskite material. And then you grow this material bulk in single crystal and melt and cool down, it forms pyrochro phase, which is undesirable phase. But when you grow exactly the same material on top of the perovskite substrate, the substrate lattice actually is forced them to form perovskite structure. Because of your atomic bonding underneath actually force them to do that. So that is what we call the substrate induced, like a metastable phase formation, which is one of the beautiful actually science and the discovery of new materials using this heteroepitaxy stabilizing metastable phase. I have a lot of examples, forming metal stereo phase. For example, strontium iridate is a very interesting the spin-orbit coupling material. Because iridium is 5D element, and then there's a strong spin-orbit coupling due to high Z number. And then that material in room temperature is in room temperature phase, is monoclinic structure. It's very complicated monoclinic structure. And then when you go very high pressure, like extremely high pressure, like 10 gigapascals and very high pressure, it actually goes to orthorhombic structure, the perovskite structure. Okay. So that means it doesn't exist perovskite structure in ambient and the ambient pressure, ambient temperature. But use this material grow on top of perovskite substrate, we can grow perovskite structure, which only possible in very high, extremely high pressure. So that is something you can actually do, allow difficult or impossible to grow a single crystal, then we can do that in this system. Okay? So now I think the perovskite is so much powerful, both technology point of view and science point of view, and we need to understand what is the perovskite is. The epitaxial growth method, and then PVD and CVD, and then described previously. A lot of names here. E is a lot of names E here, right? Okay, that's epitaxy. And then vapor phase epitaxy, metal, organic, chemical, vapor deposition, MOCVD, OMP, OMVCE, or molecular beam epitaxy, MBE. So this epitaxy is a variation of the name, and as long as you have registered growth using these different techniques of it. The way of epitaxy works here, and then there's two types of epitaxy in terms of actual process point of view, is real in situ type epitaxy we do, or we have a solid phase epitaxy. And somebody yesterday asked me about the Zoll-gel process. The Zoll-gel process is solid state epitaxy, solid phase epitaxy, because it actually grows solid state and nuclei at the interface and then grow on top. But all this reaction is due to bulk diffusion. It's not really surface diffusion. But what we actually doing in this most of the experiment we do, and then my presentation, is a molecular process or atomic process that occur at the growing surface area, not bulk diffusion and only surface area. And same as those described in PVD, CVD, but much greater control. So what that means is your atom comes down from your source material. Okay? The source is a flux, is either sputtering, molecular beam like evaporation, or pulse laser deposition, or chemical process, anything you provide the flux. And this incoming flux is all the atoms or molecules, and lay down on the surface, and then something happens, okay, then atoms. But there's a lot of process. It will come down and dissolve without doing anything, because there's tons of atoms come down, and they never happen, just dissolve, and then just go to vapor. But some of them is lay down and do something, okay? So because of this atom coming down to the surface, some energy. Okay, this energy has many different types of energy. One is thermal energy, because your temperature of source is very high temperature, and thermal energy is very small. That's why it's evaporation or MBE, much more gentle process, because the energy is only less than few eV. It's a very, very small energy. In contrast, sputtering use a very high energy acceleration of argon ion. So when you knock out these atoms or ions, that has a very high energy sometimes. It's because the energy of the ions range of 50 to sometimes 200-300 eV, which is very high. Otherwise, you cannot knock it out. And then the outcoming the particles, the high energy. So the particles come down here, and we have kinetic energy, and when you touch here, this kinetic energy or thermal energy actually use some kind of motion or diffusion. At the same time, the substrate material, you heat this up, high temperature. Okay? the substrate is high enough, and temperature, thermal energy is high enough because temperature is high, then the thermal energy is enough energy to diffuse on the surface. So atoms lay down, and then atom has to find right location to form the crystalline lattice. Okay? So that's a process. You need time, and you need some energy. You need atomic site. Really, you like to go. So, for example, perovskite structure, ABO3 structure. Your ABO3. So A type of cation goes to A site. B type cation goes to B site. You cannot go A site or B site. You have that is what we call N-type site. And you want to make sure those enough time to form those things. And then so what the process is, this is actually substrate. These atoms already aligned quite well. These atoms come down, some of them dissociation, and some of them start to nucleate. Some of them move to the edge region and attach to the other one. So a lot of things can happen. But you have incoming atoms. There's a surface diffusion is one of the important factor. Nucleation is important here. And then island growth. And then this is also step flow growth. Step flow growth, step is atoms is actually go the edge of it. Next atom come here. Next atom come here. Then this island, a step actually grow here, grow here, grow here. Step moves. You understand that? Step start to move and gradually move. That's step flow growth. Island growth, just making some nucleation island, and you have another island growth here, and then forming island. And sometimes you grow another island on top. So sometimes you make a pancake shape, like the birthday cake. You know birthday cake, multi-layer birthday cake? You're forming like a multi-layer birthday cake depending on how the growth mode changes. But fundamental, it's important in particular growth. You have to understand actual process, how atoms lay down and move and then find the right place. And a lot of parameters, and you have to understand this fundamental process. So introduction epitaxial growth, you have amorphous growth, just lay down, okay, without any energy required. Just go whatever position, then there's amorphous state. Usually when you grow material at room temperature, like all the perovskite material, without heating, you end up with kind of amorphous phase. Okay? This amorphous phase, when you go high temperature, like 8 or 900 degrees C, and start to nucleate here and grow and grow and grow, forming epitaxial material, that's we call solid phase epitaxy. And then you have island growth. You have island growth. You have this island, individual island nucleate, and then merge together in forming more flat. But when you go higher surface mobility, atoms move very fast on the surface, then it actually atom motion is much faster than nucleation of a separate island. Then you grow the step flow growth, like this step grow and grow and grow. Once the step move completely here, then you form another steps and then flow here. So it continuously, you just multiple steps moves. Okay, this step flow growth. And the step flow growth is the most ideal, the growth mode, because you don't actually nucleate the multiple layers. It's always your surface, a beautifully initial state of steps and maintain continuous steps. Okay, that's something is a very ideal growth. But not, in order to do that, you need a high surface mobility, which means you have to go either high temperature or you have a certain material system and atoms diffusivity on the surface much faster. Okay, so you have to understand that this surface diffusion, why we can grow the thin films epitaxially, single crystal material, very low temperature. Because this one requires only surface diffusion, not bulk diffusion. And surface diffusion, when you have atom lay down here, you don't have to push all the atoms move to the next step. In bulk diffusion, your atoms all the lattice point. And the size of atom I'm going to move to the next jump is big. So you have to open up and go to next, and open and next. So that requires a lot of energy, and then that's why very high temperature needed. The surface diffusion, basically, you don't have to open this a free surface on that. Only you have to overcome the energy. It's a small binding energy between this atom to the surface. Okay? You have to overcome this binding energy, go to the next step, because your atoms like to have even one bonding rather than attach to all surroundings. So it's a very low energy is required. Okay? So you have range of the mobility of the surface mobility. You can amorphous to all the way step flow growth. And a lot of growth is in between somewhere here, and then that's something we are going to show. So surface energy important factor too. So when you grow the material, sometimes material grow flat, sometimes material grow like a bubble like this. And this is due to surface energy. Okay? So you know that water droplet, hydrophobic, hydrophilic, this is all surface energy issue. And then it's exactly same thing applies in epitaxy. So when you form this epitaxial layer, is a vacuum or oxygen environment, whatever, the surface energy between the nucleus and the gas, and surface energy substrate and the gas, and surface energy between these two, so forming some kind of wetting angle, which is all you know about this wet angle. And then surface is a kind of defect, so it costs some energy to create the surface, and then the largest surface volume ratio. So universe is divided into the smallest particle, and then otherwise, because you don't have a surface energy issue. Compound with high surface energy tends to minimize the surface area, deposit a surface with low surface energy. Okay, this is water or wax. Okay, the water droplet on the oil paper, and then it forming like this. And then you have a low surface energy, and then maximize the surface area and deposit with a high surface energy. It's an oil on water. Okay, when you drop the water, and then oil spread on water. Okay, so this is you want to have a large surface area flat when you have a surface energy is low, because it don't cost that much large surface area. The same thing here is that your temperature, outside temperature is very cold. Okay, you come to Wisconsin, it's cold. Then you go out, you don't want to lose heat, so you want to shrink your body like this. But the temperature outside is comfortable, you will just open and then maximize your surface area. Okay, it's similar thing. The surface energy is very similar to that kind of concept. So surface energy actually affects growth mode. So whenever this is a different type of growth mode, and you have very flat this kind of growth mode, and depending on the surface energy ratio, and then it is all the ratio of this, and then you have either pancake shape or flat like this. Okay, so that's something general rule is surface energy and surface surface as the surface energy, and then mobility. Those are very important. So mobility itself is a kinetics, and surface energy thermodynamics. But thermodynamics and kinetics both are plays a role. But that's not all your consideration of epitaxy. As I said, when you grow material on top of A material to B material, you have always lattice match. Okay, lattice mismatch. So your thin layer like this, and then you try to accommodate lattice of the underlying substrate and accommodating it without any defects at all. Okay, that's simply compress or stretch to accommodate underlying substrate. So that means elastically deformed to match in plane lattice parameter of substrate. For example, in your barium titanate on strontium titanate, barium titanate lattice parameter is bigger than strontium titanate. So when you lay down the barium titanate on top, you either grow like bulk-like, completely laxed, or you can be compressively strained and then coherently grow. This is what we call coherently grown strain thin film. Or you have this lattice parameter is bigger than this, so you have maybe 10 strontium titanate lattice or 9 barium titanate fits, and then that's where you have dislocation forms. So this dislocation is the extra edge dislocation to accommodate different lattice parameters. What happens is, when you grow from this coherent, same material, grow thicker and thicker, then you compress this, then you build up large elastic energy. Okay? You press it. You compress, but you have to compress many layers. Then you have a lot of energy required. At some point, I cannot do that. So then you relax. Okay? So that is some critical thickness. You can have grow this kind of growth to this kind of relaxed growth. So this is called coherent, or this one is either partially coherent or incoherent growth. So you have two different types of things. So when you actually study strain engineering, there's a large amount of strain engineering, and this is required. And also, you want to study intrinsic properties. You don't want to have this kind of dislocations or any defects. These defects is scattering centers, all these things. So ideally, you want to have this one, but there's some limitation growing this material. So heteroepitaxy permit the fabrication dissimilar material on the same substrate, but the strain in the growing film depends on thickness and mismatch. So that means your mismatch, this one is large, then your coherency can grow here is only very, very thin, because you have to consume a lot of elastic energy. But lattice mismatch is very, very tiny, then you can grow very thick without any relaxation. Okay? So that is some kind of rule, and then this is all well studied in the metals and semiconductors. But I think it's applied, same thing applied in the oxide materials, but I think a little different from actual, the quantitatively is a little different. So thick film will revert to the unstrained. The unstrained means it's like a complete lax, which means an incoherent growth, and then lattice parameter, some misfit dislocation in interface with the substrate, there's misfit dislocation. Okay? So we have coherent or incoherent, strained and relaxed. So you have a name, is terminology is different. So how you know which one is which when you grow thin films? Many ways you can tell, many ways you can determine the either coherent or incoherent. There are many ways of characterization. One simple way characterization, okay, look at the real space, looks like image, look at the cross-sectional TM, and cross-sectional TM shows all the atoms. Okay? You look at all the atoms, and then sometimes you see this kind of dislocation. You count all the atoms, you draw the line, okay? Draw the line, all the lines. At some point, one line is missing. Okay? Then it clearly shows this one is a relaxed. And then sometimes I see these kind of dislocations every 10, every 5, every 20, I can see those things. And that is clearly shows, okay, dislocation, relax, and this mismatch. Okay, that's one way to do. And then another way to do, you measure, is X-ray diffraction. When you do X-ray diffraction, you measurement X-ray diffraction, X-ray can measure lattice parameters, both out of plane or in plane, you can measure those. Okay? We'll talk about that later in other X-ray type of lectures. And then you can measure out of plane of the film, in plane of the film, out of plane substrate, in plane film, you can measure all four. You can separate all four of those and by X-ray diffraction. So if that's the case, this lattice parameter of in plane, those two, exactly same. That means coherent. And out of plane lattice parameter, when you measure, looks like a bigger than bulk because you actually stretch it, and you know that. When you have a completely relaxed case, the in-plane lattice parameter is different, but in-plane lattice parameter same as a bulk, which means completely relaxed. But sometimes it's not completely relaxed, you're partially relaxed. So the value of this value is not really like this, not really like a bulk, somewhere in between. So there's a partially actually relaxed, partially coherent system. Okay? So we have a many way consideration of epitaxy. So here's one interesting test of lattice mismatch, how film grow. And then this is one interesting model system. And chemistry is very different, very similar. So to pick this example of strontium luthenate, calcium luthenate, and this is the end compound of metallic oxide, which is a very important metallic oxide, strontium luthenate, calcium luthenate. And then lattice parameter of this strontium luthenate is a pseudo-cubic lattice parameter. Okay, just ignore this one. This is also a big one. So we just use a pseudo-cubic lattice parameter. And then pseudo-cubic lattice parameter, strontium luthenate, is the biggest, 3.93 angstrom. Why? Calcium luthenate, lattice parameter, roughly 3.85 angstrom. Okay, you have two different directions. It's different because orthotomic structure, but roughly 3.84 average. You have a roughly 3.93 to 3.83, like 0.1 angstrom difference. Okay, that's a quite big in terms of lattice point of view. Is a quite big difference. And why this is different? The strontium is bigger, calcium is smaller. You look at the periodic table, and that's what a lot of your chemistry when you do epitaxy or design materials. You look at the periodic table, calcium small, strontium bigger, barium bigger. So that's why you put it in bigger cations, lattice get bigger. When you get the bigger or smaller, sometimes you cannot accommodate this one, then you start to rotate, octahedral start to rotate. That's what I talked about. Remember that? Octahedral rotation, and then you have atoms, you have a stable configuration. You have not only expand, you have some other distortion happens. Okay, so that's some very, when you have a distortion happens, your band splitting, and you have many things happen. Okay, so, but this is a completely solid solution. Pure strontium luthenate, pure calcium luthenate, complete solid solution. So when you add alloy system here, lattice parameter continuously increase or continuous decrease. So we pick here, so in between, this value is somewhere in between. Okay? And then you use this one, sulfate material is three different sulfate material, strontium titanate, neodymium gallate, and lanthanum aluminate, and large lattice parameter or small lattice parameter and in between. Then you can add a complete matrix of how the film grows, where it lacks, and what the surface morphology. You can visualize this epitaxy. Okay, I'm going to show this is a good example visualization what conceptually how lattice mismatch plays a role in the film growth. So look at this, 3.93, and this strontium titanate, and this one is which one is bigger, and this one and this one. And this one is smaller than this, right? So that means this one is compressive. Okay, so compressive means sulfate lattice parameter is bigger than this, that's a plus. But when you look at the calcium luthenate, the lattice parameter is actually smaller than this. Okay, how much smaller? Roughly 1.5% or 1.9% smaller. And then because the lattice parameter of this one is actually much larger than this, that's why this one is a tensile. Okay, so you have this a tensile and there's a compressive, but you have lanthanum aluminate. All three of those, because of this lattice parameter, all of them is actually bigger than lanthanum aluminate. So you have a change of sign of strain and magnitude of strain. You look at how this grows, and you can really see a beautiful mapping of this. So, but we have to consider not only lattice parameter, you have to consider thermal expansion coefficient. Because when you image or measurements or this thing, you measure at room temperature. But all the growth happens at high temperature. So when you cool down, your lattice changes thermally, then you have to add the thermal expansion coefficient on top of the lattice mismatch due to this the lattice parameter. Okay, so that's a two component. But these are all same perovskite structure. So all perovskite structure, thermal expansion coefficients are about the same in terms of lattice direction. But for example, silicon or metals is different. Silicon doesn't shrink that much. And that's why any film grow oxide on silicon, you have tensile strain because they stretch it. Because when you cool down, substrate does not want to shrink. But film shrink, then you stretch it. Okay, that's what happens. So you have preparation of the surface morphology of strontium titanate, okay, on top of different substrate. Can you see that? How much different? Here, strontium titanate, and then on top of this substrate. This substrate is initially you have a preparation substrate atomically flat, beautiful steps. You lay down this one, and that one. Can you see the difference? This one, very nice step structure. This one is a messy structure. Why? This one, just simple strontium luthenate, very small lattice mismatch, a large lattice mismatch, and that's why this one doesn't work. And then here, neodymium gallate, somewhere in between, but it's larger than this, so not going to be as good as this. So we have I'm sorry, we did this way, okay, this way. You got it? We did this way. So same material, strontium titanate substrate, this one, that one, and this one. Okay? And then you'll see this one and that one is quite nice, but this one is bad because you look at the lattice mismatch is less than 1%, but this one more than 1%. At some point it relaxes, and then it actually surface morphology is messed up. Okay? So we did this kind of study. But you can also do this kind of study, you can complete this mapping. So let's try to change of this neodymium gallate substrate. Okay, so neodymium gallate is that one. Neodymium gallate is that one. Okay, what happened here? So neodymium gallate is a larger lattice mismatch, a smaller lattice mismatch here. So you expect this one is bad, this one can be good. So you look at this bad and good. Can you see that? So here you start forming kind of pancake things, relaxation and then nucleation. But here is a quite nice step structures maintained, and that's because your lattice mismatch is quite small, and then this one is large. If you go here, simple, you expect this one is going to be all bad, and then it's all bad. Okay? And then substrate itself is still nice step structure, but lanthanum aluminate has twins. That's why you have a twin structure, but this is all bad surface area. So now you know epitaxy is very sensitive to lattice parameters, even though it's all three, strontium luthenate, calcium luthenate, strontium calcium luthenate, all same kind of chemistry and similar, the same kind of orthonomic structure. But you see, is this kind of mapping, and then you know what is the range you can grow coherently in smooth surface based on lattice mismatch and then other components. Okay? So that is something. Now you can actually see that the lattice mismatch strain less than 1%. It's all less than 1%. This one and that one and that one. So less than 1%. A nice step low growth structure, but greater than 1%, 3D growth is parallel surface. Okay? So that's something is you have to really work not only like this chemical material is chemistry similar, but you have to consider that. Okay, so now we have lattice mismatch growth, place strain energy, and then you're forming self energy. But you have this pseudomorphic growth, we call this one is like a coherent growth. And then here what is the actual critical thickness. Here, what we did, you fix the thickness of the thin film, same thickness. You have all use 50 nanometer or 30 nanometer thick. You fix the thickness. But even this one looks smoother, but when you grow very thick, and eventually this one looks like that. Because at some point, your strain energy is big, and your dislocation forms and grow 3D balls. Okay? So it's not only the lattice mismatch, you have another factor is thickness. Okay? So this thickness we call critical thickness, where these two contributions are equal, which means strain energy and self energy. The film thinner than critical thickness, the elastically deform and dislocation free and grow coherently. And above this thicker film and forming misfit dislocation, and it forms what is incoherent growth. So how do you predict this critical thickness? Okay? So critical thickness actually studied in semiconductor very detailed. And the equation looks complicated, but I think it is energy calculation, but thermodynamic calculation. And from this, a lot of terms here, the Burgers factor of dislocation, and then film shear modulus here, modulus, and then you have a film thickness H, and then this B is complicated function of the compliance, and then the interfacial strain. You have a lot of terms, but I think we have to consider Poisson's ratio and misfit. This F is how much of misfit percentage of it. So you have all this equation, classical treatment. This we call Matthew-Black's equation. It's a well-known equation. And then this one is treatment of competitive between elastic strain energy and dislocation energy, because you're forming dislocation, and dislocation actually create energy. So you have elastic energy. Which one is bigger? Do you want to have a defect in generating energy, or you have elastic energy is more bigger? So I have a competing between those two. Okay, elastic energy is so big, I better give dislocation energy. Okay, so that goes competing energy comes. So when you do that, so you have some kind of plot your critical thickness as a function of like the germanium concentration, which means the lattice parameter of this. When you grow more and more germanium, lattice parameter bigger and bigger. So your lattice is much bigger, your critical thickness gets smaller and smaller. Okay, that's a typical curve here. So when you go lattice match very small, and you can grow 1 micron no problem. But when you grow, the lattice mismatch is large like this, then you can grow less than 0.1 microns. Okay, so that's some kind of follows very well Matthew-Black's equation. And then the semiconductors, germanium silicon, because when you add the germanium, lattice parameter changes, and then silicon. The same diamond crystal structure, they can expand and shrink depending on concentration, like calcium strontium luteinate. And then this is what it shows. And the critical thickness versus misfit function here, and same thing here. The mismatch get bigger and bigger, and the critical thickness gets smaller and smaller. Okay? So that is important factor. But in oxide thin films, does it happen exactly same way? Or oxide thin films is not? And the general trend is same, but in oxide thin films is different. Because this is only consideration of thermodynamic consideration, which is energy only. But in reality, have you ever learned thermodynamics and kinetics? Have you learned this both too? The thermodynamics only can tell is the final states. Energetically, for example, I have piece of aluminum, piece of silicon. And thermodynamics only predict the silicon turn to all SiO2. Okay? But aluminum, you have the building material, aluminum sash, building material, aluminum. And then thermodynamically, all aluminum is supposed to be all aluminum oxide. The ceramic aluminum oxide, like a white ceramic like this, or sapphire, like aluminum oxide. Why stays aluminum? because energetically, thermodynamic final state is aluminum oxide, but it takes so long to get aluminum oxide because your diffusion of aluminum oxygen through the aluminum oxide is so slow at room temperature. It takes millions and billions of years to go, all the oxygen goes in to make aluminum oxide. And that determines the kinetics. The kinetics tells how its time scale is involved, and then thermodynamics does not consider time scale, only final state. And then here is same thing. When you grow thin films, and then thermodynamically predict this number, but it does not relax because you do not have enough kinetic energy to form the dislocation. With some strong barrier forming dislocation, then it doesn't form. So that's what we have to consider, that one. So other defects in the epitaxial growth is not only dislocations and then things like that, but you also form point defects. Okay, you remember yesterday I talked about the point defect, oxygen vacancies, anti-site disorder. That's all the point defects. But sometimes you create point defects to accommodate this lattice mismatch. So what that means is, okay, rather than you creating dislocation, I would generate point defect, make a lattice parameter get bigger or smaller to accommodate this. So certain systems place those things. One of the good examples is calcium luthenate, is anti-site calcium luthenate, and making calcium luthenate bigger. You make it bigger, you can accommodate your lattice mismatch with the strontium titate big one. And then lanthanum cobaltate, creating oxygen vacancy here. And then rather than this is a cation disorder, but the oxygen vacancies make this lattice get bigger or smaller to accommodate. So there's a lot of important plays. Point defect and often observed in equilibrium concentration here is equilibrium concentration. But dislocation is always bad because of electron-hole recombination in semiconductors. But dislocation and the mismatched substrate growth is performed beyond the pseudomorphic limit, and then dislocations propagate the growing layer and kill the device performance, many of them. But in the physics point of view, all these dislocations is lower the mobility, and then you actually mask the intrinsic property. So I think you have to, and also you realize that your surface morphology is get worse. Okay, so you want to make sure and then you understand it. So this is one example of the calcium luthenate, and then you're accommodating large lattice mismatch, and then actually creating calcium is a ruthenium anti-site, and make a volume get bigger and match that very well. So what time is it now? Let me just. So we have about 1 hour so far. Okay, so I'm going to give a real example of this strain engineering in barium titanate in the next lecture. And before then, I'd like to take your questions first. Then I want to move to this exciting and the strain engineering by heterotaxy and the enhancement of ferroelectricity. But it's a lot of interesting approach how we actually understand and the ferroelectricity in the strain systems. So let me ask you questions. One way I can do it is I can speed up this one a little longer, more short break, and then come back, depending on what you want. And then I can cover this. Then I have another one, atomic layer, and then other examples. I can cover few good examples of epitaxy. And then I have other example is interesting is heterotaxy, the unconventional, the heterotaxy to solve the problem. So I'm going to share that one specific example. So let me just invite some questions from you guys. Then otherwise I'm going to move to this next section, next lecture. What is it? Any questions about the fundamentals of epitaxy? No question?
The minimum thickness that we can grow through epitaxy technique.
Minimum thickness
that we can get through this epitaxy technique?
Epitaxy technique, minimum thickness. How do you know the minimum thickness of this? That's your question?
What is the minimum thickness which could be achieved through this technique?
Epitaxy, minimum thickness. One monolayer. One monolayer. Yeah. So the minimum thickness can do is one monolayer is roughly 2 angstrom. 2 angstrom. And then whether 2 angstrom is fully covered 100%, or 2 angstrom is nominal 2 angstrom is covered the island, and that is another issue. So, for example, when you grow this strontium luthenate, I mean that's what we have studied is because we are a lot of interesting physics study in dimensionality. You heard of dimensionality? Have you heard physics study? When you get dimension get smaller and smaller, you have a new phenomena happens. Okay, so we call in superconductivity a dimensional crossover.
For FPSC single layer, it has a totally different superconducting properties than in the bulk and single crystal.
Exactly, yeah. So that's also something on one monolayer, iron selenide, is superconducting temperature, like in one of group claim 100 Kelvin. Yeah. And then a bulk material is like less than or like a 10 Kelvin or very low. And then still the debating that 100 Kelvin is one, but at least the people agree that 50 Kelvin superconductor significant enhancement of this, and only happens one monolayer iron selenide. And then that is either is a dimensional crossover or interfacial superconductivity, and that's another issue of the physics. But at least we can go thinner and thinner. At some point, you have something new, and or narrow and narrow, something happen, and nanoparticles. Some of the silicon nanoparticles is not optically is interesting, but nanoparticles and the gold nanoparticles is very interesting in terms of the optical properties. The same thing. So in here, you can grow thinner down to 2 angstrom, but that can be done only elemental source. But if you have complex materials like composite target, the minimum building block is 4 angstrom. Because you provide A cation, B cation at the same time, your building block cannot be 2 angstrom. You grow the unit cell by unit cell. Okay, unit cell by unit cell, which means your gross building block is this with a building block. Okay, so when you look at all the step height are roughly 4 angstrom. But if you can really control this layer and this layer separately, okay, either strontium oxide or ruthenium oxide separate source, then you can make a 2 angstrom building block. So the minimum control thickness is 2 angstrom. Like iron selenide is just a binary one, so it's a one monolayer, which is basically single layer superconductivity. Okay, so we talk about the next one is interfacial, the phenomena of 2D electron gas. I think that's why we need atom layer control. But I think this is a background of like a heteroepitaxy and lattice mismatch in a lot of surface energy consideration. But I think that's enough background you can understand what the heteroepitaxy is. So I'm going to continue if you have energy to do that. I'm going to finish this. It's 2 lectures combined and can break and come back other one. So because I have to leave around 1:30 or something, so I can just without having lunch and go ahead. It's okay with you guys? Okay, great. All right. So the heteroepitaxy of barium titanate is one of the great examples of strain engineering in perovskite. Okay. So I briefly introduced this ferroelectricity, and ferroelectricity comes from off-center of titanium and barium titanate tetragonal system. And then when you apply strain and you elongate this, when you elongate it, this position of titanium atom displacement can be much further. That actually enhancement of remnant polarization, and at the same time, your energy barrier to coming back to paraelectric state is much higher, so that is very stable up to very high temperature. Okay, that's a basic hypothesis of this strain engineering. So we use here, look at the lattice parameter, and then we already done calcium luthenate and strontium luthenate, calcium strontium luthenate. I gave you example. Barium titanate lattice parameter is bigger than substrate. and this one 3.9 angstrom. And strontium luthenate, roughly 3.93 angstrom. This one larger than this. When you grow this one on top, and you have to compress it. Okay, so this one, thin film actually has compressive strain because you accommodate underlying tile here. Tile is smaller tile. I want to put large tile. You have to compress it, and this is even more compressive. Okay, so 4.0 angstrom to 3.9 angstrom is very large lattice mismatch, and then this lattice mismatch is too big, so you cannot really grow these thick films, reasonably thick films, without relaxation. This is a very similar case like we have seen strontium luthenate on lanthanum aluminate. You know the large lattice mismatch and relaxation. So you can grow in reality. You can grow maybe 10 unit cell. You grow 10 unit cell, or like more than 10 unit cell, you start to relax. 10 unit cell is only 40 angstrom, like 4 nanometers. Okay? So that's too thin to electrically measure this. Very hard to measure 10 nanometer electrically measurement, but can be done. That's what I show. PFM measurement, electrical measurement. I show the nanoscale strontium titan point defect. What I show, roughly 12 unit cell, roughly 4.8 nanometers, and we are able to measure this. So when you have this kind of configuration, then this one should have compressive strain and polarization, and then temperature can go high. So when you look at this massive complexity equation, and then you expect very similar curve. Remember that I curve show you? This curve is very similar to this curve. Okay? Thickness, this is the critical thickness versus lattice mismatch. And that's what you show here. Your lattice mismatch here, okay, strain, and versus critical thickness. And then you put this information, all the elastic information and the Berg spectra, and then you get this kind of curve, which means let's look at 1% of strain. 1% of strain, you get the relaxation is roughly less than 100 angstrom. Okay? Less than 100 angstrom is a 1% strain. If you go to barium titanate to strontium titanate, you see that, okay, it's one. The 2.5% is very large. Then relaxation happens, what? 10 angstrom or 20 angstrom. Okay, 20 angstrom with only 5 unit cell. Okay, only 5 unit cell, it relax. But in reality, it grow more than twice. As I said, 40 angstrom, even thicker than 40 angstrom, still fully coherent. And then we have tested with other substrate. Okay, I'll talk about these 2 data points. And then this one, gadolinium scandate, and then dysprosium scandate, or dysprosium scandate here, and gadolinium scandate here, substrate. And lattice mismatch like 1% or 1.7%. And the relaxation here is basically about 100 angstrom. But in reality, you can grow more than 1,000 angstrom. What happened? It's magic, right? It's 10 times more you can grow without any relaxation. How did you test it? We use the X-ray diffraction. Okay, you X-ray diffraction, we can tell what the lattice parameter is fully coherent or not. We can test it. So we actually look at this, and this equation is generally correct. Okay, this follows this line, but absolute value is not correct. So this is a good guideline, but it's not necessary to correct absolutely number-wise. So in this region, based on this massive relaxity equation, in this region, all relaxed. Below this region, all coherent. But it's a new curve, maybe curve follow here, and then region of the coherent growth, strain film, region can be broader. Okay? So now, this is very encouraging. Okay, now very encouraging because you can actually expand this. You can strain study much wider range of it. Okay? In reality, we can do it. So this is some kind of phase diagram. People predict depending on strain, what kind of phases forms, and then you read the papers, the theory papers. A lot of interesting theory papers, but some theory work is relevant and useful. Some of them is not very relevant to your experiment. So you have to know how to screen those and we also extract the information what you experimentally important. And then we ended up is calculating this one for our own important calculation. So what we did here is calculation of barium titanate is what happened as a function of strain. Looks very complicated. Okay? It's very complicated because not only showing paraelectric cubic structure or structure in the underneath, you have a barium titanate structure, tetragonal structure, but at the same time you're creating all the different symmetry of it. There are different phases. And then this is an actual barium titanate phase diagram as a function of temperature and function of strain. But you want to have a more simple diagram. We just want to know is phase change in temperature rather than phase. We don't care phase. We want to know what the phase change in temperature. So you have these two, and gallium scandate is called scandate, and those substrate is actually made new. There's a crystal growth done, and then the growth of thin films, and then PLD grown and MD grown thin films, and we have taken data and then fits within the range, and that's what it is. So look at this. It's a very important, this is very useful for all your research. Okay? This is a literature is basically adding and more substrate, and then this is very handy. Okay? So here, some of the materials you study. So these are black ones. Okay, here, lanthanum strontium gallate, lanthanum aluminate. Here, maybe a smaller one, lanthanum aluminate, and then even smaller one, and then neodymium gallate. And the largest one, you can actually have lanthanum scandate, but with lanthanum scandate, you cannot grow single crystal. So now, largest substrate and the precision scandate, and then people trying to make this region too, because some of those materials you need a larger lattice mismatch, like a barium bismuth oxide superconductor, and then or barium stanate, which is high electron mobility transparent conductors. Those things in this range, and then you don't have substrate really match with this, so you have to make a new substrate. That's what some other researchers and trying to make a new single crystal substrate in that region. And then one approach we did, and the simple perovskite like this, we couldn't find that large lattice parameter. So next step we're trying to do double perovskite. Anybody I think mentioned here working on double perovskite? Who is working on double perovskite? Okay, double perovskite. Double perovskite usually has a large lattice parameters, and then simple perovskite, and then you're trying to make those single crystal substrate, and then it's hard, but I think that's another attempt. Those things can go here. Okay, largest mismatch. But this is the most range of lattice parameter, and then barium titanate is sitting where? It's here. The barium titanate is sitting right here, 4 angstrom range, and then strontium titanate is so small, then you need to find the lattice parameter close to this. So that's why gallium scandate, this was scandate, and that's developed, and that's not very good because potassium tantalate, when you heat it up, potassium comes out to the surface, and the film doesn't grow very well. So it's not necessary like lattice parameter in the table is useful, but those two are very useful ones. Okay? So you can see all different elements here, like the PMMPT. I'm going to talk about the piezoelectric material, and then here other types of material. Even 3.95 angstrom here around that range here, you have barium 1 to 2, barium iron arsenide is superconductor lattice parameter around here, so you can grow epitaxially on strontium titanate power 2. Okay, so that's something you have very handy, and then maybe this is useful. And the lead PZT, and depending on composition of the zirconium titanium ratio, when you go pure lead titanate, you go here. You go lead zirconate, go to here. So you have a quite wide range of lattice parameter depending on composition. Okay? So now I'm going to talk about titanate growing these two and how it happens. Okay? So these are single crystals, new single crystals, and they grown by this Daryl Schlum's, and now it's Cornell, and then in Germany, Institute of Crystal Growth, and they actually made this single crystal, this was scanned and gallium scandate, because the substrate is not available, and then you give up, you try something. Okay? So that's why the experimental work is do you want to do your experiment only given condition, or you want to make something your own? You make your own, then you're the first one actually can demonstrate, or you can actually understand and discover something. But you have available, and then everybody can do it. It's as long as you have an idea and you have resources, and you can do it. So the growing this one, Chokrovsky grown single crystal, and orientation measure, and cutting crystal substrate, and then you grow the thin films. And then you have to measure the lattice parameters very carefully as a function of temperature, because we want to know real lattice parameter at growth temperature, down low temperature. You actually study this. So it's not just growing the material and that's it. We trust it. I think you have to prove it. You have to measure your own. So functional temperature, and the strontium titanate, this Boltzmann scanning, gallium scandate, gallium titanate, looks slope is very similar. Okay? So that means, okay, slope is very similar, and I think I can use this data, this room temperature lattice parameter data is good enough to first approximation. Okay? That's one. And then the way of this kind of measurement, I think that this one needs more learning of the X-ray diffraction, but I'm going to briefly talk about this X-ray diffraction. So when you grow thin films, and then I understand you have powder diffractometer here, not single crystal. You have a single crystal diffractometer here to Chi system. I heard that, Bruker system. Is that correct?
Yes.
Okay, Chi system. But that is not designed for thin film diffraction. I think it's used a point focus. Okay, point focus. And then your powder diffractometer uses a line focus. It's a line focus, and then maybe very long. And then they have a much better angular resolution, but very long, the beam. And point focus, you rotate the tube to make a point focus to focus your single crystal. Because the single crystal is very tiny, and then you don't want to long elongated beam because you throw away most of them. So you have to have a beam with a circular shape. So why you have this kind of line focus and point focus, and then your tungsten filament is in the X-ray tube. Is a tungsten filament coming. Okay, any tungsten filament like coil shape, right? And looks like this. Okay, looks like this. And then your tungsten filament shaped like this. And you hit it anode, the copper anode. Okay, when you hit it here, then X-ray coming low takeoff angle, and X-ray coming this way looks like a line. Okay, can you see it looks like line? But X-ray coming that direction looks like a point. Okay, so use this region of the X-ray will be a point focus. That's single crystal diffraction. And use this kind of beam is a line focus. So that's why your X-ray tube, you rotate X-ray tube. You have two windows, Berlin window in your X-ray tube. You rotate it, and you have a different optics. Okay, that's the basic setup. Okay, but the problem of the powder diffractometer, you have only two motors. Okay, which motor? Do you know which motor? Remember? Your goniometer of this, your theta, 2 theta, well, 2 angle motors. Okay, so that means you have only angular theta 2 theta motion, which works very well for powder, but single crystal or thin films does not work. That's why you got single crystal diffractometer. Your motor is attached under the cradle on top. The cradle this is cradle, and on top And this is what we call theta 2 theta motor. So this outside the big one is a 2 theta angle. And on top of that is mounting this rotation, the theta. So this looks like your X-ray diffractometer, the two-dimensional. Okay, only moving that direction. Okay, but you actually have additional one here. This is what we call cradle. The cradle, the cradle has angular is rotation of this one. You're spinning this. Okay, you're spinning this. We call phi. And this one angle moves like this. Okay, this is a chi. Okay, chi angle and phi angle. You allow you to move your sample all the directions. So that means you can access planes, not only planes aligned to the surface, you can access all the planes other direction. I think I'm going to talk about that later, but I think I'm just giving some very simple description of the full circle machine. And then single crystal diffraction is basically a piece of small single crystal. You rotate this, access all the Bragg conditions, and to find the actual intensity and then angle and then orientation matrix, and then what you find is determination of crystal structure. But thin films is a little different, and then use all the four circles, but your thin film geometry is like a flat surface, not like bulk like this. And then flat surface, you have a clearly, you mount your surface, a film, and you have orientation of that direction, and that direction. You have all defined. Once you know all defined, then you can access inside of this thin film all the orientation of this. And then it's a very challenging initially, especially low symmetry material system, but you can actually determine both the epitaxy arrangement, in plane, out of plane, your strain information, coherent or incoherent, you have how good crystalline quality ball, rocking curve, you have a lot of information you can get. But this thin film geometry here, you allow you to access and then different orientation and epitaxy of thin films. But this one is, in order to really study this kind of things, we need to go high temperature. When you increase the high temperature, you need a temperature cell. So this X-ray, you attach this high temperature cell, and this high temperature can go 900 degrees Celsius. So attach the sample in the full circle X-ray diffractometer, and you heat it up, and then you look at X-ray diffraction, and then both in plane, 2 theta direction, but you also measure the chi. You measure chi angle, which means, as I mentioned, the sample moved this way. So the way of doing it, okay, this is a sample sitting like this, and then theta motion is an X-ray beam coming in this way and that way. Theta is this. Okay, theta motion this. Chi is this. Phi is that. You have 3 motions. And at the same time, your detector here, detector also moves like this. Usually detector moves and then your sample moves at the same time. So that's your powder diffractometer, you have only this. Okay, powder diffractometer, only this. But thin film diffraction, you have this, you have this. That allows you to full access of this. Okay, so here you use this, attach this on the high temperature cell and on the full circle. Then you can access both X-ray diffractometer here, barium titanate, and get substrate, gadolinium scandate, and strontium luteinate. You have all the spots, that Bragg conditions, and Bragg diffractions. And then angle here, you can see the separation of this. And then normally, all your diffractometer use a point detector, which means your detector only can measure that small angle. Okay, so that's why we call point detector. But here we use the air detector, which means the air detector is large. So you detect it, all of them, the two-dimensional. Why you want to do that? Because when you ramp up temperature from room temperature 900 degrees C. You scan each of them, full scan like you do, it takes forever because you have to accessing each temperature. But in here, you just ramp up, capture the whole risk profile space at the same time. Okay, so then you look at image like this. When you heat it up high temperature, and the barium titanate, this one, it gets split or single, and depending on the splitting and single, you have either tetragonal or you have the cubic, and then you also measure from the off-axis deflection, you measure the in-plane lattice parameter as well. Not the out-of-plane lattice parameter or in-plane lattice parameter. Okay, I'll talk about that later. This may be too complicated for this one, but I'll talk about how you determine in-plane lattice parameter. So this is a whole map of how the phase transition happens. So for example, let's look at this one. Single crystals. Okay, single crystals. Single crystal has a phase transition around 150 degrees Celsius. And then your 150 degrees Celsius here, below that temperature, okay, you see that? You see this kind of splitting of these two? Okay. At room temperature, you have this A domain and C domain because your tetragonal C is longer than A, and that's why your two of them is split. But when you go higher and higher temperature, around the phase transition temperature, 126 degrees Celsius, and these two merge it, go to 1. Okay? This one shows very clear phase transition of bulk. And then same thing, this one is a 002, is also splitting of 2, and 2 close to each other, go to 1. But look at this, barium titanate and gallium scandate, when you heat it up 600 degrees C, it maintained 2. What does that mean? This one is maintained, it's a substrate and film. You have one peak here, it's a monodomain, it's single monodomain. And here is single monodomain, the substrate. You measure, this lattice parameter is out-of-plane lattice parameter. See how this lattice parameter changes as a function of temperature. Is it linear or looks like a bending? You have bending, then you start to see you have a phase transition. So look at this single crystal. You can actually see both of them because your twins, you have both twins can access it from the X-ray diffraction. But thin films is everything monodomain. Your outer plane is C. You cannot access A and D. So you can only see one lattice parameter. So this is C, and you have A. Okay, your A is completely coherent with the substrate. Okay, you have a substrate and film is on top of each other. Can you see this one, Mark? Okay, on top of each other, same. This one is a disposing scandate, and the gallium scandate. Gallium scandate is substrate, a circle is the substrate, and then maybe this behind one is a film. Is everything on top of each other. That means it's a fully coherent lattice parameter, in-plane lattice parameter is fully coherent. But out-of-plane lattice parameter is not linear like this. A linear is actually going here and bend and go like this. And bend, go like this. And then it's similar to this one. This is the indication of phase transition. Okay? This is a structural phase transition coming from cubic to tetragonal phase transition, and you see that. You understand this one clearly? Okay. So you have a phase transition, very clear here. And then this is not all. You want to measure is really it's a center titanium atom. It's off center. That's the remnant operation coming from. You remember that? You look at this tetragonal state. Your titanium ion is the center, off center. This is called non-central symmetric. And very similar to what I talked about polar metal. Remember the polar metal I talked about? And the polar metal is also non-central symmetric. And the way you determine this by what? SHG measurement. Remember? So you do SHG measurement as a function of temperature and measure this, and then you see barium titanate gallium scandate is actually has a phase transition around 400 degrees Celsius. And above here, and then you start to see is like a low, and then here, large signal, the phase transition. So that is another indirect evidence of the phase transition. So you can see the 700 degrees C, and then this is a non-polar or central symmetric, and we go 400 degrees C, still polar, and 50 degrees C, very large polar, and there's a polar plot. So that is some kind of test of this strain engineering, and then it's an enhancement of ferroelectricity. It's a quite large scale here. Okay, so that's something, and then we talked about. So let me just here. So when you look at the barium titanate, you look at the surface, strontium lucite and barium titanate, we have no dislocation. You have dislocation, usual lines here, and then it's fully coherent and absolutely no dislocation. And then this one is consistent with the actual lattice parameter measurement X-ray diffractometer. Okay? So I'm going to stop it here, and then this strain fundamental epitaxy. Then I'm going to go next one is interfaces in situ control, and how that is important, because when you go lower dimension, I think that is really critical. And then I can have another quick lecture on the unconventional, the strain epitaxy measurement. Okay? All right, so now is, what time is it? Okay, 11. So 1.5 hours we had. So we have any questions? Maybe have a tea break. Do you want to ask a question? Which one you prefer? I think it's too long. Maybe you have a losing your concentration. More questions? All right, then let's stop and then take a break and come back here, and maybe do another hour and a half continuous lecture. Then I can take the questions after that. Maybe I can leave around the 1:30 or something. Then half hour. Is that good? Okay. All right. Sounds good.
अभी आधे घंटे का लाइव गिराओगे फिर? हाँ अभी तो रोक लो, क्या अभी तो 15-20 मिनट।